Alright, so that's the SN2. On to the other reaction, again, which you just did while this one was going. Again, this took a lot longer, so meanwhile, you worked on this reaction. Alright, so here's the SN1. Does anybody know how this mechanism works? So, we have an alcohol in solution, okay? Is OH a very good leaving group? Absolutely not. OH is not a very good leaving group. But if you guys have been working on your homework, you'll notice that an alcohol in with acid can become protonated. And then, is that a good leaving group? Let's just see. So let's say we've got some H3O plus in there. Okay. We can go and get protonated. Okay, and this is true of all alcohols in solution. We can get protonated, and now, is this a good leaving group? Absolutely, especially because, what do we form? What degree of a carbocation? A tertiary carbocation. Nice. Okay, and now we have ammonium chloride and ammonium bromide in solution. Okay, so these actually look like they're salts again, NH4 plus Cl minus, NH4 plus Br minus. Okay, so now we can either have the chloride or the bromide go back in, so I'm just going to leave it ambiguous, nucleophile minus, so we'll say Br minus or Cl minus can go back in and attack to give us either product. Okay, so that's the mechanism of this reaction. Again, the OH is not a good leaving group, but if you throw it in with some acid, it does become a good leaving group, only after protonation, right? Because alcohols have lone pairs, they can act as bases. So they can go get protonated. Now we have our protonated alcohol, which is a good leaving group, especially because we form a tertiary carbocation, and we have the nucleophile. And really quick, guys, what is the rate determining step of this reaction? Acid-base reactions are not very fast. Remember, here's our basic SN1 mechanism. What's the rate determining step? The leaving group leaving. So here's our RDS. It becomes important later. Okay, and this is the one you subjected to NMR. You put it in an NMR tube with some deuterated chloroform. So now we need a brief introduction to NMR. You guys are going to have a whole big lecture on NMR next week, so we'll just briefly go over the basic logistics. And in here, what we do is we subject our sample to a big magnetic field, okay, a big old magnetic field. And the thing is, the protons in our sample, and a few of carbons, but mostly the protons in our sample kind of act as little magnets, okay? So when we apply a magnetic field to our protons, the little magnets that are the protons can either align with or against the magnetic field, okay? And actually when they align against the magnetic field, it's a little bit higher in energy. And so what we can do then is when we apply the magnetic field, we can actually detect the amount of energy it takes to kind of flip one of those magnets of the protons, okay? So the protons to go from aligned to not aligned with the magnet takes a certain amount of energy, and that exact amount of energy gets absorbed by the proton, and that's what's actually detected by our detector in the NMR, okay? So then we get peaks that correspond to the different sets of protons in our sample, okay? So that's what we get in the readout, okay? We get peaks, again, that correspond to the different sets of protons in our sample. And so we can actually get a lot from these peaks, and we'll learn all about that next week. But this is actually just what we're going to be looking at, just kind of this is a very small window of the entire proton spectrum. And so these peaks actually correspond to these protons right here. Okay, this one is of the chloride. Whoops. 1, 2, 3. 1, 2, 3. It's these protons right here. Okay? They are singlets. We'll learn why they are singlets. We can actually get lots of different splitting patterns in the NMR, in the proton NMR. But today, again, we're just looking at this focused part of the spectrum because this is all we need to look at today. So you can see too that I have put these numbers underneath Each of these peaks correspond to the area underneath these peaks. I just randomly set this one to 50 because we're going to be needing these numbers. And so normally though, these correspond to the number of hydrogens in your sample. So if we had the whole spectrum and we put these numbers here, it's called integrating it. If we integrated it appropriately, this would show about 6 and this would show about 6 because they correspond to 6 protons each. But again, I just set this one to 50 so we can use these numbers because now we need to see how much of each of these compounds are in our sample. Just like we did before, the GC actually gave us nice peaks that corresponded to each compound. Here, that's pretty much what we're going to do as well, but we have to figure out the percentages of each ourselves, okay? So to do that, again, here is the area for one of our samples, and here's the area for the other one. These aren't exact percentages because you can see that they do not add up to 100, so we have to scale them appropriately. And this isn't hard at all. All we have to do is add up these two numbers, okay? So this one, for instance, will be 50. It's the part over the whole, right? 50 over 50 plus 43.5. Okay, this is the part over the whole times 100%. That's all we have to do. Okay, so this equals 50 over 93.5 times 100%, and we get 53%. Okay, so 53% of our sample corresponds to this bromide. Okay, and so if we just do the math, the other 47% corresponds to our chloride. Okay, and so this is also pretty indicative of normal data. So here's some class data. This is what other people got. Okay, again, all we did was take the part over the whole, just do the math simply for your sample. Just take, again, the number here divided by the total number of the two peaks. Okay, so the total area of the two peaks, and you get your percentage if you multiply it by 100. And so this is other people's data. You can see it's roughly, if we take the average, it's literally 50-50. These are percentages. Okay, so you pretty much get a 1-to-1 ratio of these two products. And so this is interesting, right? Because before we did not get a 1-to-1 ratio. Okay, before we got a lot more iodide instead of the chloride product. Okay, but here we get about a 1-to-1 ratio. Everybody did. Okay, 1-to-1 ratio in products. So why? Why? Because again, what's different here? Right, we still have the same leaving group. What's different? The bromide or the chloride, and they're both in our solution here. And so which one of these should be the better nucleophile? Again, look back to your notes. First off, let's talk about electronegativity. Which one is less electronegative? The bromide is less electronegative, which again means it's not holding its electrons too tight, and the electrons can go and do their nucleophilic attack. So this guy should be the better nucleophile. Again, 1, because it's less electronegative. But also, is it bigger or smaller than chloride? It's bigger, which means again it's more polarizable, which is again what we want. And more polarizable. So again, if we were doing the same thing as before, we should have seen that we had more bromide than chloride. So why don't we? Why don't we see more bromide product than chloride? Instead, we get a 1-to-1 mixture. The question is why? And the answer lies in the mechanism. Okay, the mechanism. Again, here we just have one step, right? It is a bimolecular reaction, right? The rate depends on both the nucleophile and the electrophile. Here, what does the rate depend upon? Okay, what's the rate determining step here? It's just the formation of the carbocation. So is the nucleophile in the transition state? No. The leaving group, or the electrophile, is the only thing in the transition state. So this is not in the rate determining step. And so it doesn't affect the rate of the reaction. Holy crap. Actual experimental evidence of the different mechanisms, right? Here in the SN2, again, the nucleophile is in the transition state of the rate determining step. It's only one step. Okay, so the rate depends on both of these, and we can see the direct nucleophilicity difference in those for the SN2. But here, we don't see a difference in nucleophilicity because the nucleophile is not part of the rate determining step. okay? So it's not involved in the rate determining step, so it doesn't affect the reaction. It doesn't affect the rate of the reaction. So that's why, again, even though we have the different nucleophiles, all that matters here is how fast this guy leaves, and he leaves at the same rate no matter what, okay? So the nucleophile does not affect the rate of this reaction, okay? Which is why then we get a nice statistical mixture of 1-to-1 of the different products. Awesome. This should be enough information for you to finish up your post lab. Let me know if you have any questions. Happy Cesar Chavez Day.